In this video, we're going to discuss Gauss-Jordan elimination. So we're going to be looking at a second method for solving systems of equations. First thing let's do, we'll set up a little bit of notation. So we're going to be writing down systems of equations quite a bit in this video. So we're going to take a system like this and we're going to come up with a shorthand way of writing it in terms of a matrix. This equation here, each equation will be represented as a row of the matrix. So the columns here are just going to represent our different variables. So x, y, we'll have this vertical bar here representing the equal signs in the system. And then over on the right side, we have our constants or our numbers. So the equation x plus 2y equals 7 becomes 1, 2, 7 when we put it into the shorthand notation. Similarly, the equation 3x plus 4y equals 15 becomes 3, 4, and 15 when we put it into the shorthand notation. Now we need one definition to get going with this section. So we'll say that a matrix is in reduced row echelon form, and we will just call that RREF for short, if 4 properties are true. So first property is that the first non-zero entry in each row should be a 1. Second property, these leading ones should have zeros everywhere else in their columns. Third property, these leading ones should move down and right. And fourth property, any 0 rows should be at the bottom of the matrix. So let's look at some examples of matrices that are in our REF and some that are not. So classic example of a matrix that is in our REF is just your identity matrix. Now, when we talk about our REF, we're only concerned with what is on the left side of the vertical bar. So notice that I've just left the right side of the vertical bar empty. It doesn't matter what numbers we have over on the right side. So just looking at the left side, yet the first non-zero entry in each row is a 1. The ones do have zeros everywhere else in their columns. So we've done all the possible elimination that we could do. Those leading ones are moving down and right, and there aren't any 0 rows, so we won't worry about that. Another example of a matrix that is in our REF would be something like this. So the first non-zero entry in each row is a 1. Those leading ones have zeros everywhere else in their columns, so that's good. The leading ones are moving down and right, so notice that they don't have to move strictly down the diagonal. It's just that as you read row by row, each one is further to the right than the previous one. So that's good. And then we've got a 0 row sitting at the bottom of the matrix. Okay, let's see another few examples. So we got one more example here of a matrix that is in our REF. So for this one, the first non-zero entry in each row is a 1. Yep. The 1 has zeros everywhere else in its column. Yep. So that just represents that we've done all the possible elimination using that pivot. The leading ones move down and right. Well, there's only one in this matrix, so that's irrelevant. And yes, we have the 0 rows grouped at the bottom. So that's great. That's in our REF. Now, a couple of examples of matrices that are not in our REF. Let's focus on what's gone wrong with these. So if we look at this example here, what's gone wrong is that we have not done all the possible elimination. So if you think of these ones here, these leading ones as being the pivots that you would have used when you did your row operations, there's a little bit more elimination we could do. We could get rid of this 1. And so the property that's not being satisfied here is property 2. We need these leading ones to have zeros everywhere else in their columns. One last example here of a matrix that is not in our REF. So let's think about our properties. The first non-zero entry in each row is a 1, so that's good. We have gotten zeros everywhere else in those columns, so that's great. The issue is that the leading ones are not moving down and right. So what's required here to get this into our REF is just a little row swap. So now let's make a connection between our REF and solving systems. So here's an example of what we'll be doing in this video. So someone's going to tell us to solve a system using Gauss-Jordan elimination, and they'll give us a system. such as the one that's written here. So what we'll do is we'll write that system in our shorthand notation. where we just let the columns represent our variables, x, y, and z. Vertical bar can represent the equal signs, and then we'll put our constants over on the right side. So we would fill in a matrix like that. And what Gauss-Jordan elimination means is we want to turn the left side of this matrix into our REF. So that's why we had that whole discussion about our REF, is just so we know what we're trying to achieve on the left side of this matrix. So essentially we want to get some leading ones, we want to do as much elimination as possible and clean up this matrix as much as possible. So we want to turn that left side into our REF using 3 operations. Okay, now these operations are going to feel familiar to us because they are the same 3 operations that we used when we were finding the inverse matrix. So let's just review the 3 different row operations that we're allowed to do. First thing we can do is we can swap 2 rows of the matrix. Second thing we can do, we can multiply or divide any row by a non-zero number. So you can say divide the top row by 3 if you like. And then the third type of operation is the operation that we use when we're trying to create a 0. And I'm just going to write this one a little differently than it is written in the notes, just to make this a little bit more intuitive. Take your current row, and you can replace it with your current row plus or minus some number times your pivot row. Now, I'm even going to write this more specifically here. I'm going to write this as current row becomes current row minus some number times the pivot row. And this number here is just whatever number you're trying to eliminate. So here's our first example. Let's solve this system using Gauss-Jordan elimination. So first thing we're going to do is we're going to write this system in the shorthand notation. Columns represent our different variables, x, y, and z. Vertical line here represents the equal signs. And then on the right side, we've got the constants. So the first equation in the system, if we just pull out the coefficients, would become 3 minus 4, 1, and then 25. Same thing for the second row, 2, 4, 1, minus 16. And then in the bottom row, notice that we have no y's, so we write 0y. And there we have the shorthand version of our system. So now we're going to think about performing our different row operations. And the order for the operations is going to feel familiar, similar to what we did when we were finding the inverse of a matrix. So first thing we are going to do is we're going to get a 1 in the upper left-hand corner, which is called the pivot. So to do that, we could either divide row 1 by 3, or even easier, we could just swap rows. So I would suggest let's swap row 1 and row 3. So everything that was in row 3 is going to come up to the top, 105.11. Everything that was in row 1 is going to head down to the bottom. So we'll just recopy that entire row, and middle row is going to stay the same. Okay, and then I usually get in the habit of circling that pivot because we're now going to use that to get zeros in the rest of that first column. So let's get zeros in the rest of column 1. That means we're going to get rid of the 2 and the 3 here. And let's think about what operations are going to be required. Well, let's think of this as going current row minus some number times our pivot row. And this number that we're using is the number that we're trying to eliminate. So if the number we're eliminating is positive, then you'll really be subtracting off some multiple of your pivot row. If the number you're trying to eliminate is negative, then you'll actually be adding on a multiple of your pivot row. So for example, to get rid of the 2 that we're seeing right here, we would go row 2 minus 2 times row 1. So our current row is row 2. That's where the 2 is. And then because it's a 2 that we're trying to eliminate, we're going to go row 2 minus 2 times row 1. Row 1 because that's where our pivot is sitting. So to get rid of the 3, we're going to go row 3 minus 3, row 1. So that's the same type of operation as we did when we were finding A inverse. So let's recopy the top row and we'll just fill in the details here. So row 2 minus 2 row 1 is going to give us 0, 4, negative 9, negative 38. And if we do row 3 minus 3 row 1, 0, negative 4, minus 14, and negative 8. So now the first column's all cleaned up. We're going to move from our previous pivot. We're going to move down and right, and we're going to create a new pivot in this position here. So to do that, we are going to take row 2 and divide by 4. So that's going to look like 0, 1, negative 9 over 4, and negative 38 over 4. So anytime you're trying to get a 1, it's usually just a matter of dividing a row through by something, or potentially swapping rows. So I'm going to recopy the top and bottom rows, and we can circle that pivot. And now we're on to the task of getting zeros in the rest of that column. So that's column 2 now, which means we need to get rid of that negative 4. So the operation that's going to get rid of the negative 4, well, the negative 4 is in row 3. Our pivot row is row 2, and the number that we're trying to eliminate is negative 4. So we need to go row 3 plus 4 row 2. So let's try the algebra here. Row 3 plus 4 row 2 is going to give us 0, 0, and then we might want to do a little bit of scratch work on the side. We're going to have minus 14 plus 4 times negative 9 over 4. Okay, so that's like saying negative 14 minus another 9 gives us negative 23. And then a little bit more scratch work on the side. We need to take negative 8 plus 4 times negative 38 over 4. So that's like negative 8 minus another 38 gives us negative 46. And the top 2 rows can just get recopied. So now columns 1 and 2 are both cleaned up. We're going to move from our previous pivot down and to the right. So this negative 23 here, we want to get a 1 in that position. So to do that, we're going to take row 3 and divide by negative 23. And that's actually going to work really nicely. We're going to have 0, 0, 1, and then a 2 over on the right side. And we'll just recopy our top 2 rows. So now we've got our pivot for the third column. And last thing we want to do is just get some zeros in that third column. So we want to get rid of the 5. And we want to get rid of the negative 9 quarters. So thinking about our operations, we would need to go row 1 minus 5 row 3. So it's current row minus the number that you're trying to eliminate times your pivot row. And our pivot row is row 3 because our 1 here is sitting in row 3. We would also need to do row 2 plus 9 quarters times row 3. And we can do both those operations at the same time. So I'll recopy our bottom row, and let's focus on the top row here. So we'll go row 1 minus 5 row 3. So that's going to give us 1, 0, 0, and then this number here is going to be 11 minus 5 times 2. So in other words, that works out to 1. And then let's try row 2 plus 9 quarters row 3. So that's going to give us 0, 1, 0. And then this number here is going to be negative 38 over 4 plus 9 quarters times whatever we have in row 3, which is 2. Okay, so if we think about how many quarters we've got negative 38 plus 18 of them. So in other words, this is minus 20 quarters, or we just call that negative 5. So we know we're done with the row operations when we've found the RREF on the left side. This is RREF because the leading entry in each row is a 1. Those 1s have zeros everywhere else in their columns. Those 1s are moving down into the right, and we don't have any 0 rows in the matrix, but if we did, they would be at the bottom. So now that we've achieved RREF, we know, okay, we're all done with the row operations, and it's just a matter of writing down the solution. So let's remember what the columns represented here. The columns were X, Y, and Z, and then over on the right side, the numbers. So if you read the first equation, it literally says 1 times X plus 0 times Y plus 0 times Z equals 1. But a faster way of saying that is just X equal 1. Similarly, the second equation, or the second row of the matrix, is just telling us the value of Y. It's saying Y equal negative 5. And then the third row of the matrix is saying Z equal 2. So there we have our solution. You could write it like this, or you could write it as an ordered triple. If you prefer, X, Y, Z equals 1, negative 5, 2, and we're done. So let's try one more example along those lines. Someone's giving us a system of equations. So first thing we're going to do is write it up in our shorthand form. We'll have columns for X, Y, and Z, and then numbers. So first equation becomes 1, 2, 2, 4. Second one, 3, 1, 4, and then a 6. Third equation has no x's in it, so we write 0x. 4 plus 4y plus 2z equals 5. Okay, so there's our system. And we're going to go about this Gauss-Jordan elimination process. So first thing we want to do is get a 1 in the upper left-hand position. That's already done for us. And then second thing we want to do is get zeros in the rest of that first column. So the operation we're going to need to do, row 2 minus 3, row 1. Remember, the pattern when you're trying to create a 0 is you take your current row, and you can think of this as just subtracting off the number that you want to eliminate times your pivot row. So if we're trying to eliminate a 3, and that 3 is sitting in row 2, then the pattern would be row 2 minus 3 times row 1. Pivot row is row 1 because that's where our 1 is sitting. So let's try that operation. Row 2 minus 3 row 1 is going to give us 0, -5, -2, -6. And the top and bottom rows are just going to get recopied at this point. So that's our first column all cleaned up. And then we move from our previous pivot, which was here, we move down into the right. And so we want to create a new pivot in this position where the -5 is. So to do that, let's take row 2 and divide it by -5. So doing that all the way across, we're going to have 0, 1, +2/5, and +6/5. And again, we can just recopy the top and bottom rows of our matrix. Okay, now that we've got our pivot here, we're going to get zeros in the rest of that column. So we need to get rid of the 2 and the 4. Okay, so let's think about getting rid of the 2. We would go current row minus 2 times our pivot row. And to get rid of the 4, current row minus 4 times our pivot row. So let's try those operations. We'll start with the top one. Row 1 minus 2 row 2 is going to look like 1, 0, and then we'll have a little bit of algebra to do here. So we need to do 2 minus 2 times 2/5. Okay, so how many fifths is that? Well, 10/5 minus 4/5 is 6/5. So we would need to do 4 minus 2 times 6/5. So that's like 20/5 minus 12/5 gives us 8/5. Middle row can just get recopied. And then we'll do our last bit of algebra here. Row 3 minus 4 row 2 is what we're going to try now. So we're going to have 0, 0, 2 minus 4 times 2/5. Okay, so that's like 10/5 minus 8/5 is going to give us 2/5. And then over on the right side, again, let's do just a little bit of rough work on the side. We'd have to do 5 minus 4 times 6/5. So that's like 25/5 minus 24/5 would give us 1/5. So now we're just going to finish up with that third column. So we want to create a pivot now in the bottom right position. So we would think about taking row 3. You'd be tempted to say row 3 divided by 2/5. But remember, when you divide by a fraction, that's like multiplying by the reciprocal. So you could say that's 5/2 times row 3. And that would give us 0, 0, 1. And then we could just think about what's going to happen on the right side. So that would be 5/2 times 1/5. Okay, so the 5s will cancel out. We'll just have 1/2 there. So just recopy the top 2 rows, and then we're going to go into our final step. So I'll circle the pivot there. Last step is just to clean up that third column, and then we're going to have our answer. So we need to get rid of this 6/5 and the 2/5 that we're seeing in that third column. So let's go row 1 minus 6/5 times our pivot row, and then row 2 minus 2/5 times our pivot row. And I think we'll see that the numbers work out pretty nicely. So let's start with this top row here. Row 1 minus 6/5 times row 3. That's going to look like 1, 0, 0. And then over on the right side, we're supposed to do 8/5 minus 6/5 times whatever we have in row 3, which is 1/2. Okay, so if we think about how many tenths do we have, this is like 16 over 10 minus 6 over 10 is 10 over 10. So let's just call that 1. And then for the second row here, we're going to go row 2 minus 2/5 times row 3. Okay, so 0, 1, 0. And then we're going to do 6/5 minus 2/5 times 1/2. So if you like, just type that into your calculator. Or if you want to practice fractions, you'd say that's 12 tenths minus 2 tenths. Gives us 10 tenths again. So again, we're getting 1. So this matrix is in our REF. That's how we know that the process stops here. So we've got our leading ones. We've got zeros everywhere else in those columns. Those leading ones are moving down and to the right. And if there were any 0 rows, they would be at the bottom of the matrix. So that's how we know that we're ready to write down our solution. And I usually find it helpful just to put the names of the variables back on at the end of the problem. So the top row, for example, is saying that 1 times x plus 0 times y plus 0 times z is equal to 1. So in other words, it's just saying x equal 1. Middle row is saying y equal 1. And bottom row is saying z equals 1/2. So there we have our solution. If you want, you can write that as an ordered triple. X, Y, Z, 1, 1, 1/2. So on to our third example here of using Gauss-Jordan elimination to solve a system. Notice that the system is already written up in the shorthand notation this time, so we don't need to do that. We just need to think about what step of the process we're on. So normally we would create a 1 in the upper left-hand corner. That's already done for us. So then our next task is to get zeros in the rest of column 1. So we want to get rid of these 2 1s that we're seeing towards the bottom of that column. So we would go current row minus our number times our pivot row. So in other words, row 2 minus row 1, and also row 3 minus row 1. So we can do both of those steps at the same time. We'll just recopy our top row here. Nothing's changing there. And let's focus on row 2 minus row 1. So that's going to look like 0, 1, 2, 3. And if we do row 3 minus row 1, 0, 2, 4, -8. All right, so that's our first column done. And let's move over to the second column now. So we move from our previous pivot, move over to down and to the right. And this is going to be the location of our new pivot. And again, just by a fluke of the numbers, this turns out to already be a 1. So I could say get a 1, but yep, that's done. So then we're going to get zeros in the rest of column 2. So the correct operations would be row 1 minus 2 row 2, and also row 3 minus 2 row 2. So let's just focus in on the bottom row because something interesting is going to happen here. So let's go row 3 minus 2 row 2, and we're going to get 0, 0, 0, minus 14. All right, so let's think about what's happening in this bottom row of the matrix. Remember that what the columns of this matrix represent are the variables, x, y, and z, and then over on the right side, we've got just some number. So if we focus in on the bottom row, what that is saying is 0x plus 0y plus 0z equals -14. And that's impossible. There are no real numbers x, y, and z out there that are going to make 0 equal to -14. So as soon as we see that impossible scenario, we say that the system, the whole system of equations, has no solution. So in other courses, you may see this phrased as the system is inconsistent. So let's look back at the system that we started with. So our system had 3 different equations. So to say that a system has no solution means that some of these equations are contradicting some of the other equations. So by saying that all 3 equations have to be satisfied, we're put in this impossible situation where there are no x, y, and z values that are going to simultaneously work for all 3 of those equations. So our answer to the problem then is just this sentence here, the system has no solution. And then let's go back to the notes and we'll talk about how to recognize this quickly when it happens. So in the notes, this is just given as a short example. If you like, you could even relabel that as a fact. So the fact says, if you see a row like this, so if you see a row like one of the following examples, then the system has no solution. So what are we looking for? We're looking for a situation where we've got all zeros to the left of the vertical bar and then something non-zero on the right side. So all zeros and then something non-zero. Or if you write that generally in words, if you have all zeros on the left side and then something non-zero on the right side, that's where you have that inconsistent situation where there simply are no values of x, y, and z that can make that true. So here's our next problem. We're going to solve using Gauss-Jordan elimination. So we've already got the 1 in the upper left. Therefore, we're going to work on getting zeros in the rest of that first column. So let's do row 2 minus row 1 and also row 3 minus row 1. Can recopy our top row, nothing's happening there. And if we do row 2 minus row 1, 0, 1, 2, 3. If we do row 3 minus row 1, 0, 2, 4, 6. All right, so that's our first column done. Then we're going to move from our previous pivot. We're going to move down and to the right. And so this 1 here, that's where we want our pivot for the next step. So in general, we would say get a 1, but that's already done. And so we're going to get zeros in the rest of column 2. So we need to get rid of these 2's that we're seeing in column 2. So current row minus the number that you're trying to eliminate times your pivot row. And for row 3, that'll look like row 3 minus 2 row 2. All right, so let's look at row 1 minus 2 row 2. That's going to look like 1, 0, negative 3, positive 3. Middle row is staying the same. So we'll recopy that. And then bottom row, row 3 minus 2 row 2, I'm going to get 0, 0, 0, 0. Okay, now it turns out that this matrix is in our REF. Let's convince ourselves that that's true. So if we go through the matrix row by row, first non-zero thing that we see in each row is a 1. So that just means, yes, you've got your pivots. And those leading ones have zeros everywhere else in their columns. So that means we've done all the possible elimination. The leading ones are moving down and to the right. So that just means we did our pivots in the correct order. And yes, we've got a row of zeros at the bottom of the matrix. So we are in our REF, and that's what tells us that the row operation process can stop. Now let's take a look at this bottom row, because this is the first time we've actually ever seen a row of zeros in a system like this. So let's focus on this. So if you had 0, 0, 0, and then you had something non-zero on the right side, that would tell you that the system has no solution. But if you see a row like 0, 0, 0, and then on the right side you see a 0, the way I interpret that is just that that row is telling us no information. That row is telling us 0 equals 0. And that's trivial. That's something that's obviously true. It doesn't help us figure out what x, y, and z are equal to. So let's just write beside this bottom row, no information. So what that means is that our system of equations has 3 variables. Remember, the variables are x, y, and z. Might be handy to label those here. But we've only really got 2 pieces of information about those variables. So what that means is that there's going to be some freedom in this system. And in particular, what that means is that we're going to have infinitely many solutions. So let's call this a fact. We're going to see this fact over the next 3 examples. The fact is that any column without a leading one gets a parameter. So let's look at the different columns for our 3 different variables here. Notice that the x column has a 1 in it. That tells us we're going to be able to solve for x. The y column has a 1 in it. That tells us we're going to be able to solve for y. but the Z column has no leading one in it. Give it a new name. Sometimes you call it K, sometimes you call it T. And what that represents is that Z is able to take on any real number value. So we've said Z equal T, and that means Z is free to take on any real number value. And based on that, we're going to figure out what X and Y have to equal. So let's look up at our system here. Let's look at that first equation. So if we translate that back into a statement about X, Y, and Z, that would say 1 times X plus 0 times Y minus 3 times Z equals 3. Okay, well, that's a bit of a long-winded way of writing it. Normally, we would just write X minus 3Z equals 3. And let's solve for X. So X equals 3 plus 3Z. And then let's use the fact that we're saying Z equals T to write X equals 3 plus 3T. So whatever the value of Z is, X is going to be 3 times that plus 3. That's what we've figured out so far. And let's do the same thing for Y. So let's look back at our system. Now we're interested in the second row here, because that's where the leading one in the Y column is. Okay, and let's see if we can do the same kind of thing. So we're going to take this highlighted row in our matrix, and we're just going to translate that back into a statement about X, Y, and Z. So that would say 1 times Y plus 2 times Z equals 3. So solve that for Y. Y equals 3 minus 2Z. And then use the fact that Z is equal to T. So Y equals 3 minus 2T would be our solution for Y. So see, now what we've got are values for X, Y, and Z that involve this parameter T. So the way we usually give our final answer then, can write it as an ordered triple, X, Y, Z. And we just say 3 plus 3T, 3 minus 2T, and T. So for any choice of real number T, you're getting a different ordered triple that solves the system. So that's our solution there, and that's where the problem stops. Now, just as a follow-up to make sure that we understood what we did here, someone might ask you for some particular solutions. So they might just say, oh, well, I'm trying to solve a physical problem and I don't care about infinitely many solutions. I just want, say, 3 solutions to the system that I know will work. So what you can do is choose any T value that you like. So you might, for example, choose T equals 0 and just plug that in all the way across. And what that will lead you to is an ordered triple of X, Y, and Z values that will work. So if we let T equal 0 and we just plug that in here, we would have the combination 3, 3, 0. If you chose a different T value, like maybe T equal 2, then you're going to get a different triple of combinations of X, Y, and Z that will work. So if you chose T equal 2, you'd get, for example, 9, -1, and 2. Now, I would also point out that most triples are not solutions. So if you just chose sort of a random combination of X, Y, and Z values, let's say you say, okay, 1, 1, 1, that's not going to solve the system. So let's say 1, 1, 1 is not a solution. If you go back and check that in the 3 equations that we started with originally, that's not going to work. So when you have infinitely many solutions, yes, there are infinitely many possible combinations of X, Y, and Z that are going to work, but that doesn't mean that every combination is going to work. So these situations where we have infinitely many solutions take a little bit of practice, and we are going to do 2 more examples just to get familiar with that process. So let's solve the following system. Again, we're going to think about getting a pivot in the upper left-hand corner. So let's take row 1 and divide it by 4. That'll give us 1, -2, 3, and then a 5. And we can recopy our bottom row. Okay, then once we get that pivot, we want to clean up the rest of that column. So we want to get rid of this 3 here by going current row minus the number that you're trying to eliminate times your pivot row. So row 2 minus 3 row 1 is going to give us 0, 7, -8, and -10. Okay, and we can recopy our top row. So at that point, we've got the first column cleaned up. And then let's move from our previous pivot down into the right. And so this 7 is going to be the location of our next pivot. So let's take row 2 and divide it by 7. So we'll have 0, 1, negative 8 over 7, and negative 10 over 7. And our top row can just get recopied there. Okay, so now we've got our pivot for the second column, and then our job is to clean up the rest of that second column. So we need to get rid of this negative 2 here. So we go current row minus the number that we're trying to eliminate. So that now becomes a plus 2 times our pivot row. Okay, so let's do a little bit of algebra, get this figured out. So row 1 plus 2 row 2 is going to give us 1, 0. And then we're going to have to go 3 plus 2 times negative 8 over 7. Okay, so let's think about how many sevenths we've got. 21 over 7 minus 16 over 7 gives us 5 over 7. And then on the right side, we'd be going 5 plus 2 times negative 10 over 7. So that's 35 over 7 minus 20 over 7 would give us 15 over 7. And we can recopy our bottom row. All right, so this matrix is in our REF. The leading non-zero entry in each row is a 1. Those ones have zeros everywhere else in their columns. So that's good. The leading ones are moving down and to the right. Also good. And we don't have any 0 rows, but if we did, they would be at the bottom of the matrix. So yep, we're in our REF, and that's how we know that we can stop with the row operations. So let's label our variables then, and we'll think about writing down our solution. Remember what we said in the previous problem. That was that if you have any column in your system that does not have a leading 1, then that variable is going to get a parameter. So notice how the Z column does not have a pivot in it. We're going to write Z equal T. And what that represents is that Z can take on any real number value. So there's no restriction on what Z can equal. And once we realize that, then we're going to have to solve for X and Y in terms of this number T. So let's remember from our previous problem how we did that. So we just take the first row of this matrix and translate it back into a statement about X, Y, and Z. So we'd say 1 times X plus 0 times Y plus 5/7 times Z equals 15 over 7. Okay, so we're going to solve that for X. X equals 15 over 7 minus 5 over 7Z. But instead of writing Z, we're going to say, well, Z equals T. So that tells us what our X value is. X is 15 over 7 minus 5 over 7 times T. And then we can use the second row of the matrix to do the same thing for Y. So the second row reads Y minus 8/7 Z is equal to negative 10 over 7. So we're going to solve this for Y. Just bring the Z term over to the other side. So we'd have Y equals negative 10 over 7 plus 8 over 7Z. And then for your final answer, instead of saying Z, just call that T. And that way we have our combination of X, Y, and Z values that are going to work. Often this will be written as an ordered triple. So you could say all the combinations of X, Y, and Z that are going to work will look like 15 over 7 minus 5 over 7t minus 10 over 7 plus 8 over 7t, comma, t. So we're going to solve this system using Gauss-Jordan elimination. First thing we want to do is create a 1 in the upper left. So let's do that by taking row 1 divided by 3. That'll give us 1, 2, 2, 4. And we'll just recopy our other 2 rows. So now that we've got that 1, we can clean up the rest of column 1 by going current row minus the number that you're trying to eliminate times your pivot row. So we'll do row 2 minus 3 row 1 and also row 3 minus 2 row 1. So I think I will recopy the top row. So we've got that there. And then let's do row 2 minus 3 row 1. So 0, 0, 2, 3 is what we're getting there. And then for the bottom row, row 3 minus 2 row 1, 0, 0, 0, 0. So first column is entirely cleaned up now. So we go from our previous pivot, we think about moving down and to the right, And we would normally want this to be the location of our next pivot. But if we think about it, we can't make this 1, at least not without undoing all of the hard work that we've already done. So there's no row swap that will help us. There's nothing we can divide through by or multiply through by that will help us. And if we try doing something like adding a multiple of another row, well, that's just going to mess up the work that we already did in column 1. So once we realize that we can't make this 1, what we do is we move further right to find our pivot. So rather than choosing this 0 as the location for our pivot, we're going to move further right, and we're going to make this 2 the location of our pivot. So to create a 1 in this position where the 2 is, let's take row 2 and divide by 2. So that's going to give us 0, 0, 1, and then 3/2 on the right side. And we can recopy our other 2 rows. So we can circle this 1, that's our pivot now for the 3rd column, and we're just going to clean up that 3rd column, and then we'll be done with the row operations. So it's really just this 2 in the upper right that we need to eliminate. We're going to go current row minus the number that we're trying to eliminate times our pivot row. So let's try that. That gives us 1, 2, 0. And then on the right side, we would have 4 minus 2 times 3/2. So that's like 4 minus 3 gives us 1. And then we can recopy our other 2 rows. So there we go. This matrix is in our REF. So let's confirm that. So you look through the different rows of the matrix. The first non-zero thing that you see in each row is a 1. Those leading ones have zeros everywhere else in their columns. So that's good. We've done all the possible elimination. Those leading ones move down and to the right. Remember that they don't need to strictly move down the diagonal, but you just need each one to be further right than the previous one. So that's great. And then we've got our 0 row at the bottom of the matrix. So yes, we're done with the row operations. And now it's just a matter of writing down our solution. So what might be helpful is just putting the names for the variables back on here. And first thing you want to think about is whether you have any columns that don't have 1s in them. Because if you have a column that doesn't have a pivot in it, then that column is going to get a parameter. So let's check out our different columns here. So the column for X has a pivot, and the column for Z has a pivot. That means we're going to be able to solve for X and Z. But notice that the column for Y has no pivot in it, and what that means is that Y is free to take on any real number. So we represent that just by giving Y a new name, like Y = T. Okay, and then we can use the 2 equations in our matrix to solve for the other variables. So the top equation says X plus 2Y = 1. So if we bring the Y over to the other side, that would say X = 1 minus 2Y. And then just use the fact that Y is equal to T to say X = 1 minus 2T would be our solution for X. Okay, and then let's look at the middle row of the matrix. Well, that's saying Z equals 3/2. So no matter what the value of Y is, Z is going to equal 3/2. Z does not depend on T. So sometimes it happens that only some of your variables will depend on your parameter. And with that, we can write down our full solution. So normally we just give our solution as an ordered triple. You can say X, Y, Z equals, well, 1 minus 2T, comma T, comma 3/2. So that would be our solution there. So each different value of T that you plug in here will give you a different ordered triple, different combination of X, Y, and Z that will solve your system. So we've now had lots of practice with Gauss-Jordan elimination. We've seen the 3 different scenarios that can happen. Most common scenario is that you've got a unique solution where there's just one combination of X, Y, and Z that will work. But occasionally you run into one of the other 2 scenarios where either you have no solution or infinitely many solutions, and we've seen how to handle those as well. Since we're now at the end of chapter 16, I wanted to talk about the 2 different methods that we've seen for solving a system. So the first method involves using the inverse matrix, and the second method involves what we did in this video, which is the row operations, or Gauss-Jordan elimination, you could say. So let's look at the first approach. The first approach, you may remember, we wrote our system in the form ax equals b, and then we solved this for x. We said x equals a inverse times b. So the benefit of this approach is that it's fast, but the downside is that it only works when a inverse exists. Some matrices don't have an inverse matrix, so you won't always be able to use this first method. So that's why we go into the slightly more complicated Gauss-Jordan elimination. The downside is that it is more work, but the upside is that it is more powerful. So that's our video on Gauss-Jordan elimination. Thanks for watching.